Hello, I'm Melinda Rose.
And I'm Laura Marshall.
And this is Light Matters for March 23, 2011. Engineers at Ohio State University have invented a microscope lens that can create a 3D image from 9 different angles simultaneously. Other 3D microscopes use multiple lenses or cameras that move around an object. The new device is the first single stationary lens able to create such images by itself. The engineer said the most beneficial part of the project is being able to see the real shape of microsamples instead of just a two-dimensional projection. 3D images were successfully recorded of the tip of a ballpoint pen, which has a diameter of about 1 millimeter, and a mini drill bit with a diameter of about 0.2 millimeters. The freeform lens could be manufactured through inexpensive traditional molding techniques and used by microelectronics and medical device manufacturers who currently use very complex machinery to view the tiny components they assemble. The lens is described in a recent issue of the Journal of the Optical Society of America A.
The organic compounds surviving in 50-million-year-old fossilized reptile skin were seen by paleontologists and geochemists for the first time in an infrared image thanks to X-rays generated at the Stanford Synchrotron radiation light source in California. The brightly colored image shows the presence of the compounds in the ancient skin of a reptile found in the rocks of the Green River Formation in Utah. This image had never before been seen by the human eye until a team led by Drs. Roy Wigilius and Phil Manning used state-of-the-art infrared technology at the University of Manchester to reveal and map the fossilized soft tissue of the beautifully preserved reptile. The infrared light causes vibrations in the fossilized skin. A map of just where these vibrations occur is made using a tiny crystal, like an old phonograph record stylus, moving from point to point in a programmable grid across the surface. At each point where the crystal touches the fossil, an infrared beam that shines through the crystal reflects off its base, but a small amount of the beam probes beyond the interface. If organic compounds are present, they absorb portions of the beam and change the reflected signal. This allows the team to non-destructively map large fossils that do not transmit or reflect the beam themselves, a revolutionary process for paleontologists who have long awaited the ability to chemically analyze rare and precious fossils without the need to remove material and destroy them.
An extremely sensitive Raman sensor that relies on a completely new architecture and fabrication technique promises to detect signs of cancer, hidden explosives, and more from samples as small as a single molecule. The technology, which employs a new approach to surface-enhanced Raman scattering, or SERS, is a major advance in a decades-long search to identify materials using the technique, in which faint light signals reflecting off an object carry a signature of its molecular composition and structure. Current Raman sensors are so weak that their use has been very limited outside of research, but the sensor developed at Princeton University significantly enhances the signal over the entire device, making it more attractive for applications such as biological and chemical sensing. It could also have many applications in medicine and industry, among others. So far, the Princeton chip is 1 billion times more sensitive than was possible without SERS boosting of Raman signals, and the sensor is uniformly sensitive, making it more reliable for use in sensing devices. The U.S. Naval Research Lab is already experimenting with a less sensitive chip to discover if the military could use the technology for detecting chemicals, biological agents, and explosives.
The way light is scattered in graphene can now be controlled, providing a new tool for the study of the single sheets of carbon that may lead to practical applications for controlling light and electronic states in nanometer-scale devices made of the material. Scientists at Lawrence Berkeley National Laboratory and the University of California, Berkeley made the first direct observation in graphene of quantum interference in Raman scattering. Raman scattering occurs in graphene and other crystals when an incoming photon excites an electron, which in turn generates a phonon together with a lower energy photon. Quantum particles are as much waves as particles, so they can interfere with one another and even with themselves. The researchers showed that light emission can be controlled by controlling these interference pathways. The results will be presented in a forthcoming issue of the journal Nature.
That's it for this edition of Light Matters. For more on any of these stories, visit Photonics.com. To subscribe to our newscast, you can click on the share icon on this video player and choose feeds to enter your subscription directly into iTunes or any other RSS program.
There are also icons to share this video via email, other websites, and on most social media sites, including Twitter and Facebook.
Please send your questions or comments to lightmatters@photonics.com. Thanks for watching, and we'll be back next week.